Hi, physics. Mr. Janowski here. This is chapter 13, homework number 3, problem number 1. And the question is about the ISS. So the ISS, the International Space Station, orbits that height above the surface of the Earth, and we have to figure out a few things about this. So let's start with step Huh. So step part A. How far is the ISS from the center of the Earth? So really what we're looking for is distance. So that's going to be something in meters. Part B, what is the orbital period of the ISS in seconds? So what is our symbol for period? It's actually going to be capital T. It's a time, it's an important time, so we give it a capital T. So it's this in seconds. And then for part C, what is the orbital period of the ISS in minutes? So T is equal to question mark minutes, so that's going to be a field goal post one. So where do we begin with this stuff? All right. So we're told, so let's get a little sketch going here. So here's the Earth, and the ISS, which looks something like this. And there's big solar panels and such. Whee! Okay. So this orbits 4.00 times 10 to the 5th meters above the surface of the Earth, which means the distance from here to here. So let me indicate that out here. So this distance, that, I'll call that the height. I mean, that kind of is what it is. So the height is equal to 4.00 times 10 to the 5th meters. And the question we're looking for is how far is the ISS from the center of the Earth? So there it is above the surface. And what's the distance to the center? Well, it's going to be that height we just found out plus this distance here, where this distance here is the radius of the Earth. So radius of Earth is equal to 6.38 times 10 to the 6th. So that's the radius of the Earth. Another symbol, by the way, for Earth, this comes up sometimes, is this. You draw a circle and you draw the lines going through it. So that would be like the equator, and this would be a line of longitude going through it. So that's a symbol for the Earth. A symbol for the sun would be that. So that would be the sun in the middle and, a planet going around the sun. But that's neither here nor there. We're trying to figure out step A, or part A. So yeah, the distance we want is going to be equal to the height plus the radius of the Earth. So it's going to be equal to 4.00 times 10 to the 5th meters plus 6.38 times 10 to the 6th meters. And if you put that in the calculator, maybe if you are comfortable enough with scientific notation, you would be able to do that without a calculator. But if not, just use the calculator. And you'll get 6.78 times 10 to the 6 meters. So you put a box around it. That's a wavy box. We solved for the right thing. We gave it the right units, so we're happy with that. So on to part B. What is the orbital period of the ISS in seconds? All right, so how can we figure that out? Oops. Is this going to fit? Yeah, this will just barely fit. So we actually have a couple of formulas for the period. We have an ugly version of Newton's version of Kepler's second law. So that is T is equal to this whole quantity 2 pi over the square root of gm, and this is times r to the 3/2 power. Yeah, so if you're not super comfortable with the calculator, that's a fairly ugly looking piece of math right there. So you can do the problem this way if you want. The advantage of doing it this way, if you're really good at the calculator, is it will just spit out the answer that is t. But instead, I'm going to show you a different way that is slightly easier to put into the calculator. So let me build a little wall right here. We're going to use the prettier version. And this is easier to put into the calculator. It's just that we're going to have to remember one extra step at the end. So the pretty version of Newton's version of Kepler's third law is this. So there's still some work to do. However, you don't have that square root in the denominator. You don't have to raise something to a fractional power. It's still work, but it's going to be a little bit easier. So let's see. If we actually do this, what are you going to get? On the top, 4 pi squared. So I would recommend learning how to use the pi button on your calculator. Then on the bottom, 6.67 times 10 to the minus 11th. And never mind the extra units because I'm trying to squeeze this all in. Times the mass of what? Is it the mass of the ISS? No, we don't even know that. It's the mass of the Earth, which is this number right here. 5.97 times 10 to the 24th. 5.97 times 10 to the 24th kilograms. And then the last thing we have to deal with is that r cubed. So what is that r? Is that the radius of the Earth? No, that's the distance from the center of the Earth. And so kind of the whole point of setting up the problem this way and giving you part A is to remind you of that thing we learned in the slides, that when you're dealing with a sphere, you have to measure from the center. So yeah, when you're doing a sphere, treat all the mass as if it's located right in the center, and make all of your measurements from the center. So that's why we had to do part A. The thing that matters is not the radius of the Earth, and it's not the height of the satellite above the surface. It's those things combined. So yeah, you do all that. Now, if you put all of that into the calculator, it's going to take a little bit of time and do the order of operations correct. You're going to get a number, and that number is going to be 308,993,00.88. Yeah, and is this our answer for t? He pauses so you can reflect and see if this is your answer for t. No, this is actually our answer for t squared. So this is t squared, which means all of this is actually in units of seconds squared. So we've almost got what we want, but we're not quite there. What you need to do is take the square root of both sides at this point. Square root, square root. So there's a couple of different ways to do that in the calculator. The way I would recommend doing it is raise it to the 1/2 power. And if you raise it to the 1/2 power, that's the same thing as taking the square root, you're going to end up with 5560 seconds is equal to the period t. So put a box around it. We solved for the right thing, we gave it the right units, and we're happy. So good. One more thing to do. The last thing to do is part C, because we have a time, and it's 5,560 seconds. But I personally am not super comfortable with dealing with units of time or lengths of time that are measured in thousands of seconds. I'd rather know this in minutes. So let's see if we can turn this into a more pedestrian, quotidian kind of unit of time. So this is going to be a field goal post thing. So we're going to start with this period given in seconds, and we want to turn it into minutes, which means we need field goal posts. And I'm writing on a slant for some reason. So yeah, I want to get out of seconds and into minutes. So seconds on the bottom, minutes on the top, and what numbers go where? Well, 1 minute is the same thing as 60 seconds. So if you do this, seconds cancel. So 5,560 times 1 divided by 60 is going to give you 92.6 minutes. And I am more comfortable with that. Yeah, that's about an hour and a half. So, yeah, that works for me. That's a more everyday kind of way of thinking about this amount of time. So, yeah, the ISS up there at that altitude, what was the altitude again? 4 times 10 to the fifth meters, so 400,000 meters above the surface. It goes around the Earth pretty quickly. It only takes it, about an hour and a half to completely orbit the Earth. So that's how you do these problems. This is a Kepler's third law problem. It's a Newton's version of Kepler's third law problem. And this time we have to solve for t. So you'll get other problems like this where you might know t and you have to solve for something else. You have to solve for the mass of the thing being orbited, or you might have to solve for the radius of the orbit. So the algebra would work out differently in those cases, but hopefully now you're starting to get the idea. And hopefully you found this helpful.